Right, you made it, the last little block of talks. So you might be wondering, how could the Chernobyl disaster possibly be relevant to you and your work? But hopefully I can convince you. I want to start with a question for you, which is, what is the worst thing your code has ever done? And why did it happen? Not the kind of the literal line of code that made it happen, but what were the real underlying reasons? What do you think about that? This is my cat. He's Elrond. And yeah, I help organize LRUG, which is the London Ruby user group. Second Monday of the month, every month. If you're ever in town, look us up. I'm currently a senior software engineer at DRW. I've only been there 3 months, so I haven't actually done anything that bad yet, I think. But in a previous job, I once sent 100,000 premium rated SMS, a text message where we actually have to pay like $1 to receive it, which was kind of bad. I realize this is the penultimate session of two long days, so I'm going to keep this relatively high level, just the essentials of what we need to understand about nuclear fission, which is this, that you have a uranium atom, it captures a neutron, that produces something that's unstable, so it splits, it fissions. It releases some byproducts, so there's some barium and krypton here, some energy, which eventually gets turned into electricity, and crucially, neutrons. If those neutrons, on average, between them hit less than one other nucleus, then the reaction will slow down and eventually die out. Greater than one neutron, and it will speed up. And there are a lot of fissions. So if you want 1 watt of thermal power, so that's about 1,000th of what a kettle does, that's 30 billion fissions per second. And each of the 4 units at Chernobyl is about 3 gigawatts of thermal power. So yeah, if you remember one thing from this little sequence is controlling the reaction is synonymous with controlling the neutrons. RBMK is the type of reactor used at Chernobyl, one of several designs that were in use in the USSR at the time. And it means high-power channel-type reactor. There were 4 units operating at Chernobyl in April 1986, and they had 2 more under construction that were never finished for obvious reasons. This is kind of a high-level schematic. You have fuel rods, so this is where the uranium is. It's encased in these kind of metal tubes. You have graphite, which is the moderator. So for reasons of basically physics, neutrons come out at very high speeds, and you need to slow them down to make them more likely to hit another nucleus and continue a reaction. And in this design, the moderator is graphite. You have control rods. These are made of something that absorbs neutrons, so you can slow down the reaction by introducing more of the rod into the core. And then you have your plumbing. So water comes in from the bottom, it heats up and boils as it passes through the reactor, and then the steam drives the turbines. And then you get power. And this is something which is more like the physical layout. So the core are these sort of graphite bricks, and there's channels pierced through them where the fuel rods, control rods, and all plumbing pass through. You have what they call the biological shields. So these are great big, 2,000-ton concrete discs with various bits of radiation-absorbing materials. And they're just held on by gravity. They're just resting on the floor beneath it, and this steel cylinder around the side. And the top one is called Elena. There's no concrete containment building in this design. At the top, you have the channels where you can insert where the control rods and fuel rods go. So you can refuel the reactor while it's running, like a zero downtime deploy. And then around the side, you have more radiation-absorbing stuff, basically sand, steel, water. And this is not a reactor vessel which encompasses the entire core. It's just a cylinder that goes around the side. And to give you an idea of the scale, this is a similar design from Leningrad, slightly older. Each one of those squares is a cover, and underneath that there's a fuel channel or a control rod or something. So it's pretty big. So designs don't exist in a vacuum. They don't exist independent of real-world constraints. It's true for reactors. It's true for software projects. So, for example, you pick a technology the team already knows, or because of the surrounding ecosystem of libraries or the community maybe. And here the things that matter are they want something that's quick to assemble. So because the core is made of these graphite bricks, you can do that on site. There's no pressure vessel because that requires some very complicated engineering, very special alloy fabrication. They want to use less enriched uranium because it's cheaper. And they want something very powerful. There's a lot of heavy industry in the Ukraine that has ever-increasing power requirements. And they do have other nuclear designs in use at the time, but they're less powerful. So what does this mean? It means it's a very big reactor, about 20 times by volume of contemporary designs from the West. And that is why there's no containment buildings, because it'd just be too expensive. I mentioned there's no pressure vessel. So instead of that, basically each fuel tube is its own pressure vessel. And the idea is that if something goes wrong, that pressure vessel, that mini pressure vessel will contain the failure. And what they've allowed for is for 1 to 2 tubes to fail. If more than that fail, then the whole reactor will go. But they just think this won't happen. It's like the Titanic. They thought they had enough hulls. And to be clear, any design has a resilience target. You might design for the loss of one availability zone, or you set a pod disruption budget in your Kubernetes cluster. But this is a pretty modest target they set themselves. They also have some flaws. They have a thing called a positive void coefficient. And what this means is that water absorbs more neutrons than steam. So if the reactor heats up, water turns to steam, fewer neutrons are absorbed, so the reactant speeds up, and then more water turns to steam, and it will speed up even more. Other designs behave the opposite way, but not this one. It's very hard to control. This is partly a function of its size. It's so big that you can have the reaction going fast in one corner, slow in another corner. It's like controlling multiple reactors all at the same time. The operators quite literally wear out the controls at their desks. It's pretty hard to work with. And it suffers from something called positive scram, which I'll explain now. So this is another very simple reactor schematic. I drew this one. I don't know if you could tell. You've got your control rods. So remember, these absorb neutrons. You insert them to slow things down. You've got the channels which they go into. These channels are filled with water, so we get steam and so on. I've not shown the actual fuel. Anyway, at some point they discovered if you put some graphite at the end of your control rods, then you get a more efficient reactor. Like, efficiency is good, so they do this. So what's wrong with that? Well, the way you shut down a reactor is you insert the control rods in as far as they'll go. They call that a scram if you do it in an emergency. So when you do this, the control rods go down, the graphite moves down as well, and this displaces water from the bottom of the reactor and replaces it with graphite. And graphite is a better moderator than water. So this speeds up the reaction instead of slowing it down for a few seconds. And as it happens, the scram process is quite slow here as well. If enough of the rods are already in, then the speed up is less noticeable. So this situation where all of the rods are out is the most dangerous. Because in this state, your emergency shutdown procedure actually increases power for a few seconds. So, this is basically, it's a spicy fire extinguisher. It shoots out gasoline before it shoots out foam or water. Now, every system has issues, has trade-offs. We've got technical debt to pay down. So the message here isn't, hey, this is not how to design a nuclear reactor. I mean, it's not that relevant to you here today. You probably have problems in your own systems. You might be not very resilient to a certain type of failure. You might rely on unmaintained software. You might have kind of very borderline DB utilization at busy times. Or maybe you have common maintenance tasks that are quite difficult or very time-consuming or error-prone. But what I actually want to talk about are cultural flaws. So problems with the organizations and the humans and how they interact. I think that's much more transferable to our work and our hobbies. So one of the problems they have is a culture of unrealistic targets and deadlines. It's your classic, congratulations, comrade, you made 1,000 tractors this year, next year, 1,500. The design itself, normally you build a small-scale prototype. Not here. The first RBMK reactor was a production-sized one. So some of the issues in the design, they predicted ahead of time, and some of them they only figured out in the field. So Leningrad suffered a partial meltdown due to the low enrichment levels. So after that, they increased the enrichment levels, but they only found that out once it actually happened. There are lots of construction defects and shortcuts. They have persistent problems with concrete quality. The roofs are supposed to be covered with a flame retardant kind of sealant, but there are shortages, so they replace it with bitumen, which is flammable. And that will become relevant later. And this is not a culture where you get rewarded for drawing attention to a problem. It's not one where you can communicate honestly. They also have a big hippo problem, so highest paid person's opinion. This is a culture where you not a culture where you question a superior. If they're above you in their pay grade, they're probably right. And the deputy chief engineer forced several key decisions in the build-up to the accident. And they have a culture of secrecy. So nuclear incidents are treated more or less like state secrets. So both from the general population, but also in between plant operators. So the lessons from the accident at Leningrad, for example, are not fully passed on to operators of other plants. This happens within plants as well. So in 1982, there's a partial meltdown of Unit 1. The people who weren't at their desk at that time, when they came in the next day and said, hey, we heard something kind of crazy happened yesterday. Stone-faced silence. No, nothing happened. Don't ask about it. When things do happen, the KGB is normally on site pretty quickly to make sure there's no fear-mongering. You could say they're more worried about escape of information than radiation. And what this means is that while at certain levels people do understand the flaws and the issues and so on, the information that filters down is very fragmented and very partial. So, for example, they know about the positive scram effect, but this is just passed down as, oh, by the way, never remove all the control rods. Not, this is a critical safety problem, just, hey, here's one of the hundreds of directives that you have to comply with, and you're already behind your schedule, but do all of them. And to be clear, in the West, people are covering up things as well. So there was an accident in a plant in the UK called Windscale. It's not quite on the same scale. Coincidentally, when I made that premium text messaging mistake, I was working for a company called KGB. No relation. Anyway, so you have a culture of, issues happen to other people. Because, for example, everyone knows about 3 Mile Island, which was a meltdown in Pennsylvania not that long before. And there have been other accidents in the West that have been discussed, so SL1, Chalk River, Windscale. But the lesson that they draw from this, or the lesson that's projected, is that, hey, this shows the dangers of decadent Western technology. But again, as I mentioned, at the right levels, they know that accidents are not just, hey, these weird corner cases that could happen, but these are things that are likely to happen on a normal operation. So, they make some design changes, but in general, they're not retrofitting them, and they're not explaining why these are important things. They're more likely to do things like this, to have this blind faith in Soviet technology. This is from a magazine called Soviet Life, which was basically a propaganda magazine they distributed in the West. This is from February 1986, so 2 months before the accident. And it's like, gleaming, shiny metal and precision technology. So a town born of the atom that refers to Pripyat, the town they built to support Chernobyl and house the staff. And the people, they're very well trained and so on. At roughly this time, the Ukrainian Minister of Power was quoted as saying the risk of a meltdown was roughly 1 in 10,000 years, which did not age well. So basically, in this operation, in this culture, failure is not an option. It's just impossible because the technology is perfect. And if you were to suggest otherwise, that would be rather disloyal. And that's a terrible thing, not just because it's not true. So they have had previous incidents that released radiation at Chernobyl. Because failure, when you can do it safely, is a very powerful learning mechanism. And if you pretend failure doesn't exist, then you're removing that learning mechanism. So the lessons from all those previous incidents and near misses and so on are not passed on. The 1982 incident at Chernobyl was very similar to one at Leningrad 7 years prior. Positive scram has been observed in the wild. It's not just a theoretical thing. So, I think they could have done with a bit more openness. All systems we all make trade-offs, and we all have corners that we've cut. We've all had incidents of some sort. It's not a weakness to admit that. It's just being honest with ourselves. Own your mistakes. I say especially if you're, higher up the ladder. It's a terrible thing to work somewhere where junior engineers believe that only junior engineers make mistakes, and that somehow one day there'll be a senior engineer and never make a mistake again. Talk about these incidents, talk about these limitations, document them widely. Resolve incidents in the open. So it's very tempting, I think, if something happens, you DM your colleague, hey, this weird thing is happening. And then that's kind of resolved, not exactly in secret, but not in the open. But actually seeing how people address a production issue can be a very powerful learning mechanism as well. And yeah, be open to new ideas as well. Listen to all the opinions in the room. That new person who's just joined, they've got a different perspective. Their ideas are interesting too. And yeah, being open is hard if you've got the KGB kind of, peering over your shoulder. But hopefully you don't have that problem. But jokes aside, it's obviously harder than just saying we're open. It's very easy to say that, but it's something that you have to lead by example and do so persistently to create that culture of psychological safety, which eventually will hopefully trickle down. I mentioned safe failure, and again, that requires some effort. I think in our industry, that's things like test suites, sandbox environments. I mean, Andre mentioned this the other day. It means having an easy way to deploy, an easy way to roll back. If you make a mistake, ideally you catch it before it makes it to production, but if it does, you want to be able to fix that thing quickly. Ideally, you don't want to have any error-prone repetitive tasks that you're going to screw up at some point. You want to kind of remove them from the equation altogether. So the accident itself, April 25th, 1986, it occurred during a test they were supposed to run before the plant went into production at all, 1983. But they're late. They're under a lot of pressure to complete it on that day because they're about to enter scheduled maintenance. So if they didn't do it today, it's going to be another year. And it's already late in the day. They're delayed for a variety of reasons. And they're testing a safety mechanism that boils down to power stations need power. It sounds silly, but it's one of the reasons why grid failures like the one they had in Spain last year and in Texas a couple of years ago are hard to fix. There's lots of equipment on site that needs power, especially coolant pumps, which are kind of important in the nuclear plant. And they make a series of unfortunate decisions. I say they, I mostly mean the deputy chief engineer. He makes a snap call to run the test at a lower power level. And remember that in this design, the lower the power level, the more unpredictable the reactor. Other staff object, but he overrules them. They have a computer system with a very unintuitive interface. And so someone makes a mistake and puts the plant into an even lower power level than it should have been in. So they pretty much shut it down by accident. And really, at this point, they should have called it a day and stopped. But they've got these deadlines. And the deputy chief engineer insists they continue. And they're struggling so hard to get the reactor going again so that they can actually test it that they withdraw all the rods. So this is that kind of loaded and cocked gun situation I mentioned earlier. And again, they know they shouldn't do this. They know it's one of the directives, never do this. But they don't know how bad it is. And they've got their boss shouting at them, so they do it. The test itself actually works fine. So the test is over, and it's time to shut things down. It's kind of disputed exactly why they pressed the emergency shutdown button, which was labeled AZ5. This is a picture from reactor 1. But they do it anyway. They remove the little seal, they lift the plastic cover, they press the button. The positive scram effect sort of kicks in, positive void feedback loop starts, and within seconds, reactivity peaks. Fuel channels rupture. There are 2 explosions within seconds. The first one blows the roof. The second one disperses even more of the core. So you've got tons of graphite, fuel channels being pulverized and sent up into the sky. The graphite core, which is very irradiated and very hot, catches fire basically immediately. This is one of the first photos of the aftermath taken 14 hours later. They knew straight away that it was bad. There are no good explosions at a nuclear power plant. But it took them a long time to accept just how bad it could be. And the people in the control bunker were basically refusing to accept the reports they were getting from the front line. 6 hours after the explosion, they were still deploying heroic efforts to try and get water pumps going again. And this is what they were trying to cool. That disc in the middle is the ELENA, the biological shield. These are the fuel bundles they were trying to pump water through. So yeah, not going to happen. And this thing just balanced at this precarious angle. It could have slipped down and caused a huge dust plume at any point. This is another angle. You've got the turbine hall, that kind of lower building on the right-hand side. You can see a bit of damage of the roof at the bottom right of the picture. This is Unit 3. So this is another independent nuclear reactor. Its roof is covered with burning graphite. And if you remember, the roof is flammable. Unit 3, incidentally, was back online December 1987, and they continued running it until December 2000. And they basically just filled all the corridors between the 2 units with concrete, made sure that people didn't do more than 1 shift in a row, shortened the shift slightly, and carried on. So it's like a legacy service you just can't get rid of. So what are they worried about? And what can go wronger? Well, quite a few things. Escape of radiation. So I mentioned there's a fire burning. It's carrying fine particles away. Winds are blowing some of it towards Moscow and eventually, obviously, towards large portions of Europe. Downwards, they're worried that this contamination will get into the water table, into the rivers, with huge implications for the rest of Ukraine. And of course, they grow a lot of food in Ukraine as well. Steam explosions. There are some water tanks in some of the basement levels. They worry that if something super hot hits that, the water will turn to steam and the whole thing will explode again. And then further criticality. Maybe no one really understands how the core will behave. This molten mess of uranium and other metals, maybe the reaction could start again. And there are still 3 other reactors on site. Don't make one good by guessing, but at the same time, keep an open mind. Whenever you're resolving an incident, don't just assume about what has happened or what hasn't happened. And beware of unintended consequences. I mean, you can't really blame them for trying lots of things at once. They are not well prepared for this type of scenario. To an extent, they're doing things because they feel like they have to do something. They came up with all sorts of theories of things they could do. For example, pumping out water so that the steam explosion couldn't happen. They thought maybe they could pump liquid nitrogen to freeze the ground. They ran a lot of helicopter flights like this one. So some of them are just observation flights, but many thousands of them were used to drop about 5,000 tons of sand, lead, clay onto the core, boron as well, to either contain radiation or stop the reaction. But they couldn't get very close, and they couldn't linger because of the very high levels of radiation, so they're just kind of throwing it into the reactor from a distance. And later expeditions showed that basically none of these materials actually made it anywhere close to where they would have been helpful. But every single flight did, however, stir up huge amounts of radioactive dust, both from the downdraft from the rotors and from the chucking, a ton of lead into the building. I mean, be prepared. It was kind of tough for them to be prepared because, I mentioned this before, they couldn't really suggest that this incident was even possible. But hopefully you don't have that problem. You can be thinking ahead of time, what happens if our database goes down? What happens if our payment provider has an outage? You can be prepared. Then the other side of any kind of incident is communication. I think it can be best summarized here as minimize at every step. The explosion itself is in the early hours of the 26th. They don't start their evacuation of Pripyat until about 36 hours later, and it's billed as a temporary evacuation. People are told to take 3 days' worth of clothes and food and so on. Spoiler alert, they never make it back home. The evacuation zone expanded multiple times. Eventually, over 100,000 people evacuated from Pripyat, over 350,000 people overall from other parts of Ukraine, Belarus, Russia, and so on. The rest of the world first finds out on the 28th. There's a nuclear plant in Forsmark in Sweden. They pick up some weird readings, and they realize that it's not coming from inside the plant they're monitoring, but from outside. And they can see where the wind is coming from. This is also the day where Moscow, the USSR starts cloud seeding flights. So this is a practice where you send some planes up, you release silver iodide and other chemicals in an attempt to make it rain. Because the idea is the rain will take all the reactive dust out of the air and is going to put it on the ground, unfortunately, because they're quite worried that some of these clouds are heading towards Moscow. There's a lot of debate whether cloud seeding actually works at all, but it did rain, and their intent was clearly there. And this is why Belarus actually gets more contamination by area than the Ukraine did, and proportionally much more. But at this point, they're still not acknowledging any sort of incident. They do later that evening. It's a 23-word statement. It doesn't mention radiation at all. There's been an incident at a plant. It actually makes the evening news. They mention an explosion the next day, and it's not until the 30th they mention radiation at all, but only to say that it's improving. At this point, the fire is still burning. The fire is not going to be put out for another week. There are still huge plumes of radioactive smoke billowing over Europe. This is from a couple of weeks later. Units 1, 2, and 3 you can mostly see. This is what they call the cascade wall. So they would crane a big metal container into place. They fill it with concrete. That means they can get a little bit closer and repeat the operation, and eventually build up this wall. They tried using robots to do it, some of the military bomb disposal robots and so on, but they just couldn't deal with the radiation and would glitch out very quickly. Somewhat chillingly, they sometimes called the humans bio-robots. Anyway, they got to about this. November 1986, this reactor 4, it's got what they eventually called the sarcophagus containing it. And this took about 100,000 people working very short shifts for this phase of the cleanup, and many more people in subsequent phases. Very few had dosimeters to get accurate records of the radiation they received. So as well as the physical cleanup, they're also worried about, or thinking about, well, who's to blame? What happened? And you might guess that the answer is not the design of the reactor, but the people who were working there. So classic show trial, the plant operators take all the blame. Conveniently, quite a lot of them are already dead. They acknowledge some possible improvements, but it's not really until the 90s that there are real discussion of the design failures. The original report is updated in 1992. I think it's a pretty safe guess that if the Soviet Union hadn't collapsed in between, there would have been many more years before all of this came to light. They did get some posthumous awards in 2008. That's nice. My take on this and kind of final main lesson is blame system and processes, not people. You know, if a junior on-call engineer makes a mistake, then the real question should be, why were they in that position without the right safety net, the right knowledge? If a mistake is easy to make, then try designing it away. Don't just add a note to a wiki page saying, by the way, don't make this mistake. Focus on the whys, not whose fault. And the language really matters, both during the incident, during any kind of post-mortem. I was not that smart for much of my life. I used to work on a system where it's very easy to deploy. You could SSH to a staging instance and then deploy to production. And yeah, one of my colleagues did that, caused an incident, and for many years we called it doing a Gary because he was the first person to do it. So this sarcophagus was a temporary solution, built at great speed out of necessity, and they knew from the start that it was not going to be the final answer. So for example, the roof of this sarcophagus is lying on, it's got these support beams, they're lying on walls damaged by the explosion. Quite quickly, water starts to leak in through the top. That water picks up contamination on its way through the building and seeps into the soil. So like any good temporary solution, it was about 20 years before they actually started work on a fix. I mean, it's a tough problem, to be fair, and also a lot of arguments about who should be paying for it, especially with the breakup of the Soviet Union. This is from 2013, during the construction process of what we call the new safe confinement. And the reason you can't see the reactor at all in this photo is because it's a couple of 100 meters to one side. They built it away from the reactor because the radiation levels are still pretty high. So this is kind of a wider view. And yeah, it's a very complicated process. Normally, if you're building a structure, you dig up the ground to make foundations. They can't do that here. The radiation levels are high, I mentioned. They also want to suspend internal cranes from the ceiling of this thing so that once it's in place, they can demolish some of the internal structures. So eventually, they got it done. They slid it across on rails. So yeah, use rails. Yeah, October 2017. And if I'd given this talk a year ago, this would be the last photo. But this happened about a year ago. A Russian drone hit it. And I think the current assessment is still there. It's about $100 million worth of damage to repair. It's still very difficult working conditions. It's not in danger of structural collapse, but an assessment from the IAEA at the end of 2025 was that it has lost its primary safety functions, including the confinement capability. It doesn't sound good to me. So on that downer of an ending, thank you very much. This book, Midnight in Chernobyl by Adam Higginbotham, was like my main original source. I highly recommend it. So it's a really good read. Yeah, and I'd love to talk to you about your disasters and anything else really. So thanks again.